When we finish, it will begin. So we could start with question 1 first, which was a question on incremental variables. So the first part was asking you to, the overall question was looking at the effect. So let's run through the question. So we gave 2 IV examples in the class. We gave the example of using the quarter of birth as an instrument for years of education, and we also looked at using level of mortality rate as an instrument for institutions by looking at the effect of institutions on GDP. So normally most questions in practice, we want to look at the effect of one variable or another, where this variable is likely to be endogenous. So it may be endogenous. So we've got some data. She collects data on alcohol consumption during pregnancy, AI. So this would be units per week of alcohol consumed during pregnancy, and then afterwards on a follow-up would collect the test scores of a child aged 6, which would be some measure of their performance at some test. Then she runs 2 different regressions. So regression 1 is just a simple univariate regression, just regresses test scores on alcohol consumption. Then another researcher suggests that including some further controls may better estimate the effect of alcohol on test scores. So she suggests years of education E, number of cigarettes smoked in a weekly cigarette smoked S, and the mother's disposable income I, and a score and a W variable whether or not a child attends a private school or not. And again we can form this linear model here. So again we've added in these control variables here. And again, as always, we just assume that our variables form an IID sequence. Okay, so we set up a particular IV question. So the first part A asked us to discuss whether AI is exogenous and comment on the sign and the likely size of the bias, if any, of the OLS estimate of beta naught 1. So what would it mean to say then, what does that mean formally? If AI was exogenous, then what would it mean? Well, if A is exogenous, AI in regression 1, exogeneity would mean essentially that the covariance of AI and the error term was equal to naught. So from the first regression, exogeneity, we know from the OLS assumption, exogeneity would be when AI is uncorrelated with UI. If this were the case, then we know that the OLS regression would be unbiased and consistent, and beta naught 1 would reflect the exogenous effect of a change in alcohol on test scores. So the question is getting at then, is it likely that alcohol consumption is unrelated to all these other factors UI which are also driving test scores? So the way to think about this is, what are the other variables which drive test scores which may be correlated with their level of alcohol consumption? And again, we've given some examples down here which will form the part of question 2. We've given some examples of these factors which may drive test scores. So it's unlikely to be exogenous because, well, if you think if a mother drinks during pregnancy, well, it's likely to be positively correlated with other factors which negatively influence health, like smoking and drug use or unhealthy eating, and possibly a more unstable environment like poor parenting skills and so on. All these other factors are likely to impact child development, and they're also going to be strongly correlated with whether a mother drinks during pregnancy. So we'd expect then to find that this doesn't hold. And again, we'd find then here, it's likely that AI, this covariance is likely to be what? Positive or negative? Well, it's likely it's going to be negative, right? Because as AI increases a little, the more, if alcohol consumption increases during pregnancy. Sorry about that. If alcohol consumption increases during pregnancy, then it's likely that these other factors they're more likely then to be in an unstable environment and more likely to possibly eat unhealthily and so on. This would mean then that has a negative effect on their test scores. These other factors are likely to be lower, which means that the UI would be smaller. So we'd find a negative correlation between A and U. So for this type of question, you'd be expected to demonstrate your knowledge of what exogeneity meant and then come up with some factors to say whether or not you'd think there would likely be a bias and talk about the sign of it. So in this case, it's pretty clear that there'll be a negative bias. In other cases, it may not be so clear. And you could maybe put forward a host of variables, some which may lead to a positive bias and some which may lead to a negative bias. But in many cases, it's the case that it's normally clear that the bias would be more one way than the other. And in this case, we would likely find a negative bias. So again, ask any questions as we go through. So the next part then, part B, if AI is likely to be, so the next part asks us whether A is likely to be exogenous here. It asks, sorry, there's a bad, it says equation 4, but it should be equation 2. So again, this should be 4, sorry. So the next part essentially says, would this variable AI be exogenous in this regression where we include this controls? Now what this says in words is in essence, have we included all these omitted factors in this regression above? So you could think in regression 1, you could think that UI includes all these other factors, omitted variables, which are driving test scores, which may be endogenous. So kind of what it's getting at here is, do we think we've controlled for all these other factors which drive test scores, which may be correlated with ability? Okay. Then it asks us again to comment on whether the OLS estimator is likely to be of a smaller or larger or the same magnitude of the corresponding OLS estimator in the original regression. Okay. Well, the way to do this then would be, so the linear model, so this should be 2 here, but it's changed the notation here. We include some extra control variables. So including these may remove some of the bias of OLS by controlling for some of these omitted factors. And we can then see whether these omitted factors were likely to be leading to a positive or a negative bias in the original regression. Namely, when we run this regression here, number 1, we could think that all these were in the error term. This would essentially then be UI here. So the question is, when we run this regression in number 1, we had all these factors here from UI, and were these leading overall to a positive or negative bias? So it's that when we include them, do we think we've taken the bias away, removed it, or so on? So again, there's not always a right and a wrong with these questions, but it's like you demonstrate your knowledge. Okay, so let's go through the factors then. So when we omitted EI, years of education, in this original regression here, we could think that it was in the error term. But what kind of bias would that have led to? Well, it's likely then beta 02, which is the effect of education on test scores. So remember, these two things have to be equal to each other. All we said is that UI could be expressed like this here, where it's got some of these factors above. So when we ran this regression, it was the case that education was having the effect beta 02. So do we think that beta 02 is going to be positive or negative? Well, it's likely that beta 02 is positive, that education has a positive effect on test scores. And it's likely, you could argue, that AI would be negatively correlated with how much somebody drank during pregnancy. You could say that more educated people would possibly on average be slightly less or more likely less to drink during pregnancy. So again, it's likely including this variable in the regression reduces the bias. And remember, there was a negative bias before. We've essentially removed one of the factors which was causing a negative bias. So including education would likely reduce some of the bias which was in the original regression, where we didn't control for education. Okay, so parental income. Well, there's two things here. What we're looking at is what's likely to be the effect of income on test scores, what's beta 03, and what's the correlation between income and ability. Well, you could argue that higher income individuals on average drink less, but again, of course, higher incomes allow the potential to drink more. So it isn't necessarily clear, but it's likely that there's going to be a negative correlation. It's likely that there's likely to be a negative correlation between income and education, and higher income individuals are probably more likely to invest in private tutors and so on and get a better education. So it's likely the effect of income on a child test score is positive. So what that means is that we've got income which has a positive effect and is negatively correlated with how much they drink. So again, including income is likely to reduce the bias in A. It's removed some of this negative bias in part A. And you can go through like this. So you can do the same thing for parental test scores. For a private school, likely private school has a positive effect on the child's test score, and likely that wealthier parents will drink less, so that there'd be a negative correlation between people who go to private schools and how much their mother drank during pregnancy. So again, it would likely reduce the bias in A. And again, it goes through all of them, right? And you could do the same thing for a number of cigarettes smoked. Likely to be a possibly strong correlation between smoking and drinking. If someone drinks a lot, they tend to smoke as well, on average more. And it's at this point, the effect of smoking on test score is questionable. You could think that it reduces them, or it may not. So it's not necessarily clear. So it's not clear whether including smoking would reduce the bias or not here. And again, it's more that you have a decent argument. There's not always a right or wrong. It's more that you understand. It's more that you understand the ideas behind this, not that there's necessarily right or wrong reason why including certain variables may do a certain thing on. Okay, so this answers part B then. So overall, it's likely that including all of these variables, controls, would control for some of these factors which are driving test scores, which may reflect the stability of their environment and so on, which may reduce some of the bias in part A, such that when we control for all these variables here, we know then that beta 01 is the effect of a change in alcohol during pregnancy, holding all these other factors fixed. This is much more likely to reflect the true effect of alcohol than in this regression here, where this is just the straight effect of alcohol for the general person in the population. This is the effect of another year of alcohol during pregnancy for someone with a fixing of the level of education, income, whether they're at a private school, and how much they smoke fixed. Okay, so that's how we interpret these. Okay, so these two are quite a wordy discussion here on these. So the next part then was more formal, and it's asking you to test the identification assumption. So part A and B ask you to talk about the bias, and the next part then goes on to looking at instruments. So it's likely then that we haven't removed all the bias here, right? In part B, you could argue we have control for some of the factors, but again, you can't really control for the stability. You can't fully control for the stability of the environment. You can't control for these other factors like diet and so on and so on. There's so many other factors which drive a person's test score, which are likely to be correlated with how much their mother drank during pregnancy. So although we might get a better picture by inputting all these controls in, it's still likely that the OLS will be downward biased. Namely, we'd overestimate the effect of drinking on test scores. So remember, the effect of drinking on test scores is the true effect is likely to be negative. So when I say that when it's downward biased means that'll be more negative. We'd find a stronger effect than was actually there. So we may find a very strong effect, negative effect, just doing OLS of alcohol on test scores. But this may be picking up some of these other factors which we've not controlled for, like stability and so on. So this would mean that we need some instruments then. And there's a big literature on this, that's actually quite interesting, that we then look at, well, we need to find some instruments. We need something which drives the change in alcohol consumption, which is not correlated with all these underlying factors that we can't measure often, which drive test score. So boiling it down, we want something which is correlated with alcohol consumption during pregnancy, but is uncorrelated with their underlying stability, their parenting skills, and so on and so on. Okay, so normally we try and find something which is kind of random or not in the person's control. And one quite clever way of doing this is, well, you can have, the researcher may have data on genetic markers. There are some genetic markers which are found to cause problems metabolizing alcohol, such that it can make people feel ill. So you could argue that this would then lead to a parent with this gene would then be likely less able to drink. It would change their level of drinking. And you could argue that people's genes are just completely random. You could argue that this happens. It's called Mendelian randomization. So there could be two genes, say. Gene 1, if person has this gene, and gene 2, where these both are genes which cause alcohol metabolism issues. Again, so then to use G1 and G2 as instruments for alcohol, assuming that all the remaining variables are exogenous. Again, and we can run the first stage. So the first stage regresses alcohol consumption on the instruments and all the controls. So the first stage is run. This is used to test the identification. The first stage is only looked at to test the identification condition. Yeah, remember when we derived the limit distribution and consistency, we have to have that there's a full rank. We have to have sufficient correlation between the instruments and the regressors. Otherwise, the limit won't exist. So again, the crucial assumption for consistency of two-stage least squares is that this full rank assumption holds. So the next part then is sorry, this should be 3 here. How can we use a first stage regression to test the hypothesis that the model is identified, i.e. that this third assumption holds, two-stage least squares 3, outlining a method along with test statistic and the corresponding limit distribution. So there's a few things here. You have to then first note, well, this is the definition of identification. Yeah, where we have the instrument now, we've got the constant, both the genes. So these are the instruments for A, and then all the controls. So we're using the controls as the instrument for themselves. So this is our instrument vector here. We've got all the controls. We've got both our instruments for an instrument for alcohol and the constant, and this is our original regressor here. So this is our regressor, and this is our instrument vector here. Okay. So then we need to then and this was one of the questions in exercise 7. So in order for this to be full rank, and you've shown this in another example, we have to have that either pi naught or pi 1 are not equal to 0. So when you work out, you could work out this matrix here, multiply x by z, work out the matrix, and if both pi naught 1 and pi naught 2 are equal to naught, in essence, it says that the instruments do not affect A, and then this instrument, this matrix here will not be full rank. Okay, and this was one of the questions in the lecture 7 tutorial. So then, to test identification, we do a joint test that both of the genes have no effect in the first stage. So we do a first stage that pi naught 1 and pi naught 2 are equal to naught. Okay, in this case then, this would not be full rank, and it would be unidentified. We wouldn't then be able to derive the consistency would break down. So we can test this by running an OLS regression in equation 3 and doing an F test that this joint restriction holds. And again, the F statistic is just, as you know from lectures 1 to 4, is this here. So we have the formula for the F statistic, and again, this is the sum of squared residuals in the restricted model, and so on. So in this case, you weren't given any numbers. You'd just be expected to outline how you do the test. So you state the assumption, what the identification assumption is. Then note that in order for it to hold, we have at least one of these has to be not equal to naught. Then you can note that you can do that by running a regression, do an F test. You can do then you get the F statistic. You then compare this relative to an F2 and n-6 being the degrees of freedom. 2 being the number of restrictions, n-6 is the degrees of freedom. So again, you get the F statistic and you do the test. If the F statistic was bigger than the critical value, you'd reject, and if it was smaller, you'd accept. Okay? So there's a few things there. First, noting that you know what the identification assumption is. Then, what it amounts to in that regression, that it's a joint test. Then, knowing that you can run an F test, do OLS, get the F statistic, and then just outline how to do the test. That's then all the steps to explaining how we test for identification in that example. Okay, so are there any questions so far? Ask a question. If you've got any questions, just write it in the chat, because I'm watching it as it goes down. Okay, so part A, we looked at just doing a straight simple regression. Is alcohol going to be exogenous? And definitely will be. Part B, we add some of these controls to try and proxy for these omitted factors which govern test score, and we argued likely that they'd remove some of this negative bias. However, it's still likely there's more variables which we can't measure, like stability and parenting skills and so on, which will drive test scores and will be correlated with alcohol. So a researcher has these genes which we argue are exogenous because they're determined at random. People don't pick their genes. And some people have genes which make them feel sick. So this should then lead, when they drink alcohol, so this should then lead to a change in alcohol behaviour, and this can be then exploited then to look at the effect of alcohol on test scores. We then tested whether genes are correlated with ability, with alcohol consumption, and we discussed formally how to test this identification sample. Intuitively, it just says that at least one of the genes has a non-zero effect on alcohol. If the gene didn't affect alcohol, then of course they'd have no informative content. They wouldn't lead to any changes in alcohol consumption. Okay. So the next part then, part D. Again, we only touched on this in lecture. I'm in the process of making a little video clip and some notes on this. But if both pi naught 1 and pi naught 2, they're both, remember, these are the effect of the genes on alcohol. If they're non-zero, which means that it's identified, but they're small, then what would be the potential issues of using two-stage least squares as instruments for A? Okay, well, there's two things here. So what's one of them, which we covered in class? There's two. The biggest problem here is what? So if pi naught, if the effects on genes on alcohol is very, very small, and you derive this in an example in the class exercise of tutorial 7, you showed that in a simple example that the variance, the asymptotic variance, the relative asymptotic variance of OLS to two-stage least squares is 1 over rho squared. Namely, as the correlation between the instruments gets smaller and smaller and smaller, the variance of two-stage least squares gets bigger and bigger and bigger and bigger. So we know one big problem is that when this is this one here, there's two problems. One of them is that the asymptotic variance increases as the correlation between the instruments and the regressor decreases. The correlation here is obviously governed by pi naught 1 and pi naught 2. As they get smaller and smaller, the correlation will decrease, and it will lead to a bigger increase in the variance. So again, obviously it says, explain briefly, you'd not be expected to derive this and so on, but you saw the intuition from a simple example. You derived the relative variance of two-stage least squares and OLS, and you showed that in a simple example with one instrument, that as the instrument correlation got smaller and smaller and smaller, the relative variances between OLS, two-stage least squares, and OLS got bigger and bigger and bigger. Okay, so this would be enough here. Another one, which we're going to talk more about in this extra video clip, is that as the correlation gets smaller and smaller, not only does the variance get bigger, but because the variance essentially becomes infinite, it leads to a non-standard distribution. Namely, the asymptotic normality breaks down. It becomes the approximation gets worse. The normal approximation gets worse and worse and worse. What I mean by that is when we derive the limit distribution of the two-stage least squares estimator, you get that you derive the square root t result times two-stage least squares minus 2 parameter. You find it becomes normal as n gets bigger. But again, in small samples, there's no guarantee of how good that approximation will be. There's no reason in small samples this approximation could be really bad. And it turns out that as the correlation between the instruments and the regressors gets smaller and smaller, the quality of this approximation gets worse and worse and worse. Namely, it requires bigger and bigger sample sizes in order for the normal approximation to work well, which is related to what's called the weak identification problem. So we're going to cover that, and I'm going to do a simulation in a video clip. So this will come out soon. So there's two things here. As the correlation between the instruments and the regressor gets smaller, the normal approximation of the small sample distribution of two-stage least squares gets worse and worse. And we're going to see this in a simulation, but you don't need to prove this. And the asymptotic variance gets bigger and bigger. And you've seen this in a simple example. So we've actually shown this result in a simple example. Okay, so they're the two problems then of having instruments which are identified but only just. So it's they're kind of very weak. It's what's known as weak identification here. Okay, so if any questions, let me know. Okay, finally then, the researcher believes that two-stage least squares in regression 2 using the genetic markers as instruments for A is likely to be biased, since she argues SI is also likely to be an endogenous variable. Okay, so again, above the question says assume exogeneity, and you run through. But of course, in reality, there could be other endogenous variables. There's no reason why you've just got one endogenous variable. So you could argue that smoking was also going to be endogenous. You may think that smoking would be related again to all these factors like negative stability and so on, which would reduce test scores, and it would be positively correlated with alcohol. It would be positively correlated with these other factors which are missing, right? So the point is that smoking is likely to be correlated with these other instability factors as well, which would then lead to a biased effect. When we run OLS, we're likely to not get a true effect of smoking on test scores, because smoking as well is also correlated to all these other factors like negative, like unhealthy diet and poor parenting skills and so on. Okay, so the next question asks you to discuss whether or not you think these particular instruments would likely to be valid or not. So in this question, again, it's more of a wordy question, but you're expected to know here what would it mean for any of them to be a valid instrument, and then you'd be expected to justify whether or not you think they would be. So the first part, there is a right or a wrong. You're expected to know in general when will an instrument be valid or not, namely, is it exogenous and is it identified? Namely, is it correlated with a variable of interest but uncorrelated with all these factors which are omitted? You'd then be expected to give an argument either or, and again that's when there's a grey area. It's more, there's no right or wrong, it's more that you make a valid point. Okay, so we're now looking at an instrument for a number of cigarettes smoked. Okay, so we want something which is correlated with how much a person smokes but is uncorrelated with other factors like diet and parenting skills and so on. Well, do we think that price? Well, again, there's no right or wrong, right? In order for it to be valid, we need that we need it to be correlated with alcohol, identified, and we need it to be uncorrelated with the error, these omitted factors. This would be the exogeneity assumption. So B is justifying its exogenous, and A is that it's identified. Well, if it's identified, we need that whatever the instrument is, and firstly we start with cigarettes. We start with the price. So the price of cigarettes, near where that person lives. Well, it's highly likely that price is going to be correlated with how much somebody smokes. So arguably, the price of cigarettes would. Yeah. So it's very likely that they're. What's going on here? Okay, he's done it the reverse way around here. So B is justifying whether it. Sorry, so he's done it the other way around here. So this would be B, just to be clear with the below. So this is done it the other way around. Okay, so part A is talking about exogeneity, and part B is talking about the identifiedness. So let's start with whether it's identified or not then. Namely, is there a correlation between correlated with SI, so there's two things. So we need to justify, do we think price is correlated? Do we think price of cigarettes is correlated with how much they smoke? Do it in B. And secondly, do we think that price is exogenous? Do we think price is correlated with these emitted factors? Well, it's likely that cigarette price is negatively correlated with smoking, which would just mean that there's a negative elasticity of demand. Again, we may argue that even though there's an effect, it might be quite small, right? Because it's often found that this price elasticity is quite inelastic due to the addictive nature of smoking. So again, there may be some effect. It's likely to be identified, but it may be a small effect. It may only be. It may not lead to a very big change in smoking. So, do we think that the price of cigarettes is exogenous? Well, you could argue the price of cigarettes would only influence behaviour of the parent through how it changes their smoking behaviour. All these other control variables they're controlled for. What this is saying is, we don't think it's unlikely that the price of cigarettes would affect the stability of the household. It's unlikely the price of cigarettes would affect their parenting skills and so on. And especially given that we've controlled for the parental income, You could argue that prices may be lower in areas where there is more poverty, for example, which could be correlated with test score. But you could argue that because it controls for the parental income, it kind of controls for that, so it takes that out of the error term. So here, really, after all the controls, it's highly unlikely the price of cigarettes has any effect apart from the effect it has on smoking and the other control variables. Highly unlikely that it affects these omitted variables like unstable environments. Okay, so we do the exact same thing then for asthma. So whether the parent has asthma or not. So this is somewhat related to the gene argument. It's a condition that the person doesn't necessarily control, which can affect how much they smoke. So part A discusses whether it's exogenous, and part B discusses whether or not it is identified. So is it identified, part B? Well, it's likely that mothers with asthma will be less likely to smoke than those that don't, since smoking can greatly exacerbate the symptoms of smoking. So it's likely to be a negative correlation between smoking and asthma. But then again, it could be the reverse, right? You could maybe argue that a person, maybe asthma can be brought on by smoking, or people that had smoking parents, so there could be a positive effect. Doesn't really matter for the identification whether the effect of smoking, or whether the effect of asthma on smoking is positive or negative. It's only that it has an effect. So is it likely that there's going to be a relationship between asthma and smoking? Yes, it's probably likely that people who have asthma will probably smoke differently to the ones that don't. So it's likely that whether or not someone has asthma will affect how much they smoke. And it doesn't really matter whether or not it's positive or a negative effect. Okay, the question of exogeneity is not as clear, right? So arguably, whether or not they have asthma has no direct impact on test scores over and above its impact on smoking, and is unlikely to be correlated with poor parenting and potentially other unhealthy lifestyle choices. So again, it'll be tenuous, it's not clear. You could maybe argue that a parent that's got other health problems, a person with asthma may likely have other health problems which may negatively impact the child development. So you could maybe think of some factors here, but again, it's more that you just make an argument. So again, there's no right or wrong here. So finally then, you could have whether or not a person has a partner that smokes or not. So we've got the exogeneity and the identified. You could argue that it's likely to be identified. You could argue that if a parent has a partner that smokes, likely to be positively correlated to whether the mother smokes. As people with similar interests kind of more likely to get together. Again, in terms of the identification, it doesn't matter whether the effect is positive or negative, but it's likely to be there, and if it is there, it's likely to be positive. Is partners' smoking behaviour likely to be exogenous? Well, probably not. Partners which smoke, etc., maybe are likely have other like unhealthy lifestyle factors which may negatively affect test scores. But then again, it may not. If it's there, it may be very, very, very small. So again, it's not clear either way. Okay, so that question was quite a somewhat wordy question. So much it's more, but you'd be expected to demonstrate your knowledge of the underlying theory, the assumptions, and then you'd be expected to tie your arguments, whatever they were, to that particular theory. So, for example, tying whether or not someone's exogenous, you know the formal definition of it, and then you go on and see whether or not in this example it would hold or not, and give examples why. And the same for identification. You state you know the assumption, and then you go through arguments for and against, and again, there's not really a right or wrong there. It's more that you put forward some argument with some validity, which shows that you understand the idea. Okay, so are there any questions on that? And again, you've got the solutions here. So part 2 is a more theoretical question. We've got a simple regression setup here. So we've got y regress on a scalar x and b naught, and the error term here. And we've got some, so x is scalar, and we've got some m by 1 instrument z. And again, so this should be just a 1 here, because we've got k is 1 here, we've got only one regressor, because x is scalar. So here is a case where we've got one regressor, and we've got potentially one or more instruments. So in class, this here is kind of the correlation, the covariance between E and Z. So in lectures, we assume that this was not. If this was not, along with the identification assumption and so on, we showed that IV would be unbiased. What this question gets at is that even if there was some endogeneity in instruments, even if some of these elements were not, which would mean that there was a correlation between the instrument and epsilon in the error term in Y, we can still show that when we form an instrument which is a sum of when we form a linear combination of these instruments, we can show that we can still get exogeneity. This is what this question was getting at, and we'll come back to this. But for now, all it says is that this correlation between E and Z is just some m by 1 vector. So this will just be a stream of numbers here. So this is just more general. It doesn't say what they are, it just says it equals to some particular vector. And again, it's an m by 1 bounded vector here. We've got the covariance matrix of the instruments, call it sigma, which is an m by m bounded matrix. A researcher then forms an instrument, called it zt star, which is some linear combination of z. So kappa is just some m by 1 vector. So kappa dash zt will just equal the sum of each element of kappa kj times zjt from j equals 1 to m. That's what this does, right? So kappa will just be k1 to km, and we're going to get times, and we're going to dash this, and we're going to get z1 to z1t to zmt. So we get this here. So this here is just a linear combination of the instruments. So in practice, kappa would just be fixed. Kappa would be some weights in a vector, and would form a linear average, some linear combination of our instrument z. So all we've done is take m potential instrument z and formed with that just one instrument, which is a linear combination of m other ones. Okay, and we can form then an IV estimator. So this notation here, kappa, just means it's a function of kappa. For every different weighting vector, we'll get a different instrument. So here it's simple because this is just a scalar. So this is just the formula for the IV estimator of a scalar, where we've got this instrument here. So it simplifies. This is just a scalar here. So we've got this. So again, we get the sum instrument times x times, and then we get the sum of z, the instrument times y. So again, this is just the IV formula evaluated at this particular instrument here. So then we just go through. In essence, it doesn't really matter what this is. We can use all our ideas, and we can work out what are the properties of this as t gets bigger under our assumptions. Okay. So the question says, state the conditions on kappa, the way we weight the matrix, pi naught, the effect of the instrument, sigma, the covariance matrix of z, and then xi, this is this kind of covariance matrix between E and Z, vector. Give the conditions such that this instrument will consistently estimate beta naught. So again, first off, we need to write down what that means. That would mean we want to find the conditions on all these variables which give us this result. So this, firstly, make clear what consistency means formally, and then we're going to show it. Okay. Well, this question didn't give you all. This question didn't say that the variables are I, D, and so on. So you'd be expected to just make the assumptions. So firstly, then we know that for consistency, we need linearity in the parameters, which is given by 1. So we have linearity given by 1. So this is 2-stage least squares 1. We have an IID assumption on our instrument semi-regressors, and again, this just makes clear this is actually just a sufficient condition. We could make weaker assumptions, but we just assume it's IID. This will allow us to use the weak law of large numbers. So again, we can make this assumption then that our variables are IID. We need that it's identified, 2-stage least squares 3. So all we're doing here is running through these these conditions needed for IV to be consistent. Well, in this case, our instrument's a scalar z, so we just need this to be not equal to naught. Remember, the general result is that this covariance matrix is full rank. Well, in this case, x is scalar, and our instrument zt star is also scalar. So it's just a scalar, and a scalar is full rank when it doesn't equal naught. So we just verify this then. We work out when this will be the case. So again, all we've done here is to plug in zt star equals kappa dash zt, and xt equals zt dash pi naught plus eta t. All we've done, multiply these together and expand them out, and you'll find this here. Okay, and again, this is just sigma here. We know that this term is not, yeah, because remember, this pi naught coefficient is the OLS coefficient. This pi naught by construction makes eta and z uncorrelated. So we know that eta and z are uncorrelated by the definition of pi naught. Remember, pi naught is the OLS coefficient, which by construction makes the error unrelated to the regressors, and the regressors here are z in the x regression. We have the covariance matrix sigma. So then we're done then. This term equals naught, so it drops out, and this is just sigma here, so we get this result here. So then we've derived this matrix here, which in this case is just a scalar, and we know by definition it's identified if this doesn't equal naught. So we just have to have that kappa, sigma and pi naught are such that this doesn't equal 0. Okay, so that's one condition. We need the identification condition to hold, and we've derived it in this particular example. Okay. Finally then, we need the exogeneity to hold. Okay, but we see here, sorry, this should be zt here. We've assumed that this covariance between E and Z is just this xi matrix, and it's bounded, and we've got sigma is bounded as well, and this is bounded also. So everything is bounded, so we can do a weak law of large numbers result. Okay, so we're going to use all this then, and we're going to see when it's consistent. Well, all we've done here is multiply and divide by 1 over t, and they'll cancel out. So all we've done in step 1 is take the definition and just divide by t in here, and divide by t in here, and they both cancel out. So this is just standard. Then we plugged in yt. So if we plug yt in here, we have yt equals xt beta naught. So again, this is just standard. Plug in at yt and expand it out. We're going to get beta naught. So the first bit will cancel, because we're going to get xt. So the first bit will drop out, and we're left with this term here. And crucially, everything revolves on the properties of this here. Okay, so you keep seeing this again and again and again. This is going to be the crucial part. This here. So then, by the IID assumption and the boundedness and the identification assumption that this scalar is not equal to naught, then we can use a weak law of large numbers result on this. Okay, so it converges to its expectation, and because the limit is full rank, namely it's a scalar and it's not equal to naught, then the inverse exists, which comes by the continuous mapping theorem. So if you use a weak law of large numbers, because the limit has full, and then when we take the inverse of this, because the limit of this matrix is full rank, it's a scalar which is not equal to naught, then the limit also exists, and we can use a continuous mapping theorem to show the inverse of the sample average converges to the inverse of the population expectation. And likewise, we can use a weak law of large numbers on this term here. Okay, we've assumed that z and epsilon is IID, and therefore we have an IID. We can use the weak law of large numbers, and again, this term here is just xi. This here is bounded because we've assumed that xi is bounded. So finally, then we've already derived this. This is just this thing here. We just now need to work out, well, what's this term here, and we can show that it's equal to kappa dash xi. Okay, so the last bit then, so this goes through a bit more detail here. The final bit then is to work out, well, what's this term, which is this part of the limit here. Well, just plug in zt star equals kappa dash zt. So plug it in. Kappa comes outside because it's fixed. And by definition, this is xi here. So you're going to get kappa dash xi, which is why we get this here. Again, and we've derived this above. So this was derived above. And we know this doesn't equal to naught by the identification assumption. So we can see then, well, when is IV biased? Well, when the IV estimator converges to beta naught. So we need this whole term to equal naught. Well, that's only going to happen when this equals naught. So the conditions that we need then is that kappa dash xi equals naught. So the two crucial conditions here are kappa dash sigma pi naught doesn't equal to naught, which will give us identification. And we have kappa dash pi, xi, sorry, equals naught, which would be exogeneity here. So all we've done here, all this does is test your understanding of deriving, using the weak law of large numbers, deriving the limit of some random variable, and then putting together everything to see, we know it's going to be consistent when it's identified, and we've worked this out, and it's going to be consistent when it's exogenous, and we've worked this out, and we've proven the result. Okay. So are there any questions on this? So I'll save this will get saved to the stream, and also don't forget I put an announcement out about the revision stream. So I'm also going to do if you put questions on the notice board, then over the holidays in January before the exams, we can hold some revision stream sessions going through the question. Okay, so I hope that was useful, and that's it. Thank you.